Hello everyone, my name is Ashish. I'm currently pursuing my BTech in Computer Science Engineering at the lovely Professional University. Today I'm going to present my DSA project, the Slider Puzzle Games built in C++ with SDL2 graphics library under the guidance of Mr. Ravikant Saucer. This project is a complete implementation of the classic 15 puzzle games where you slide number tiles to arrange them in order. But more importantly, this project demonstrates 5 core data structures and algorithm concepts which I will explain live as you so you the code and the running the game. Let's begin. Let me start my project. So at the top, here the VS Code with my project file shadow.puzzle.cpp. This entire project is written in a single C++ file. Let me give you a quick overview of how it's structured. At the top, you can see the included statements. I'm including SDL2 for graphics and the C++ standard library. I'm including vectors, stack, queue, unordered sets, and string. Each one of these is a specific data structures I am using in the project, not randomly but with a purpose. Below, uh, below, there are my constants. Grid size is 4, meaning of 4 by 4. Both tiles px is 120 pixels per file, and this control the window size. And then comes the move structures, the board class, the rendering functions, finally the main functions with the SDL2 event loop. Let, let me now run the games and explain everything live. So this is my terminal and I'm going to run this program. I'm using G++ with C++ 17 standard. The flag tells the compiler with SDL2 is SDL2 files are located installed via homebrew. Let me uh, So after the successful compilation, this is our game where we have to arrange the all the tiles from 1 to 15 in the segment with like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we can play this game like this, and first we have to put 1 here, then 2, then 3, then 4, then 5, like this. So you can see the 4 by 4 grid with 15 number tiles shuffled randomly and one blank space. The status bar at the bottom so my move counter. Let me now explain what is happening behind the scenes. So uh, the first and the most fundamental data structure is a 2D vector. Declare having the study vector. From here we have declared this like this. The first and the most fundamental data structure is a 2D vector declared here. Vector of int. This is a table of 4 by 4 row and column, exactly matching what you see on the screen, like this. Each cell stores either the tiles number from 1 to 15 or 0, which represent the blank space. So when you look at the game window, every color tile you can see correspond to one cell in the 2D vector holding the number. Now look at the tile add function. So let me explain the first this slide tile add function. Uh, when I click a tile, the program first check if if the if the tile is adjacent to the blank. It calculates the absolute difference of row and column between the tile and blank. If the sum equals 1, the tile is valid never. Then it simply does a swap. The tile valued and a 0 value switch position in the grid. This is why I choose a 2D vector over a flat only row and column, indexing mapping naturally and directly onto the visual grid. making the code clean and instructive. Switch back game. See, I click a tile into the blank space. That was one swap operation in the 2D vector. The second data structures is a stack declared here as uh, a stack of move. A stack works on the last in and first out principle. The last item you put in the first one you take out. Look at the move struct. Look at the move struct. It store four integers: the row and the column of the tile before it moves, and the row and the column of the blank before it moves. Every time the player makes a valid slide, the line pushes a move onto the stack, recording where the tiles came from and where the blank was. The stack grow by one element with each move. Now look at the undo function. This where undo is called, it pops the top element, the most recent move, and reverse it. It swap those two positions back and restore the blank's location. Why a stack and not a queue? Because undo must reverse the most recent move first. This is exactly what last in and first out gives you. A queue would reverse your oldest move first, which is completely wrong for an undo feature. So I'm switching to my game and I will show you the five move. I made five moves like this: first, second, third, fourth, and this fifth. Watch the tiles go back one by one in the reverse order. That is the stack popping element once at a time. Now I have to explain why this shuffle the function. Now let me explain the shuffle mechanism, which is one of the most interesting algorithm decisions in this project. The common mistake would be the randomly placed numbers 1 to 15th in the grid, but here is a mathematical fact about the 15 puzzle. Exactly half of all possible random arrangements can never be solved, no matter how many moves we make. So if you randomly shuffle, you will give the players an unsolved puzzle 50% of the time. A shuffle function avoid the completely. Look at this, it starts from the solved board and then performs 300 random legal slides. Legal means it only moves a tile that is actually adjacent to the blank, the same kind of move the players make. Since every one of those 300 moves is valid, since every one of those 300 moves is valid reversible operation, the resulting board is mathematically guaranteed to be solvable because it could, in theory, just reverse 300 moves to get back to the solved state. I also have a separate solvability check using inversion counting, which verify this theorem independently using a nested loop algorithm. You can see it printing the console. It's a true, confirming our shuffle is valid. And we have to press R to reshuffle the game. Point to the console output. Like when we pressing R, then see the shuffle. See the shuffle. Now I will explain uh, the fourth concept is breadth for searching using a queue and a headset. This is the most advanced DSA concept in this project. Uh, the idea is this: think of every possible arrangements of 15 tiles as a node in the graph, and think of every legal tiles slide as an edge connecting two nodes. The entire puzzle is really a massive graph of board configurations. The functions verify reachable within them. Performs a BFS traversal of this graph starting from the current board to confirm the goal state is reachable within a certain depth. Here is the queue of pair of a string and int. The string is the encoded board state, the int is the current depth, and the queue insert the explore states in order of increasing distance. That is the FIFO property of a queue, first in, first out. Here is the hash set study and order set of this, which is an order set of the string. Every time, um, every time we visit a state, we insert a string encoding here. Before visiting any neighbor, we check the set. If the state is already there, we skip it. This prevents infinite loops because tile slides are reversible. Without this, you would just keep going back and forth forever. Why BFS and not DFS? Because BFS explore level by level, all states reachable in one move, then two moves, then three, then gives as a meaningful depth bound reachability guarantee. DFS would dive deep down the path first and could miss nearby solution entirely. Now let me show a full live demo of this game. The board is shuffled. Now we can shuffle by press R. Just press R and you can see this is shuffle. I can move tiles by clicking them into the mouse. Only tiles adjacent to the blank will slide. I can also use the arrow key or WSD for keyboard control, like this arrow key we can use for this. And also we can press U for undo and pop the stacks and reverse my the last move. And I can also press R to the reshuffle. The goal is to arrange tiles 1 through 15 in order, reading left to right, top to bottom, with the blank in a bottom right corner. When I achieve that, the program declares it. This is the itsold function. Works the entire grid, like this is the itsold function. And work this is the insert function. Work the entire grid and confirms every cell matches the expected value, and a green sold balance appears. One last thing worth mentoring. I did not use any external font library to draw these numbers. SDL2 does not include text rendering by default. That requires an additional library called SDL2. Instead, I built a custom mini font render here. Each digit 0 to 9 is stored as a 3 by 5 pixel grid. You can see these arrays. A value of 1 means draw a filled rectangle. A value of 0 means leave it blank. The way I render my number from 1 to 15 is only SDL2's basic rectangle drawing commands with 0 additional dependencies. Now I have to summarize this project. To summarize, this project implements a classic 15's gaming in C++ with SDL2. It applies 5 core DSA concept in a real working system. Number one, a 2D vector stores the board map directly to the visual grid. Number two, a stack records moves history in a default order to the power to the um, undo feature. Number three, a queue which has a drives a BFS status space search to verify board reachability, treating every board configuration as a node and an implement graph. Number four, an inversion counting algorithm applies the classic n puzzle parity theorem to mathematically verify solvability. And the number five, string serialization encodes 2D grid into the single hashable key for a constant times state lookups. Every structure was chosen because it was a natural fit for the problem it solves. Not to inflate the count, the project was built under the guidance of Mr. Ravi Kant. Thank you for watching.